Okay, good morning everyone. In this first hour of today's lecture, we're going to talk about model-driven engineering in general. I'm going to give you a quick introduction before and hopefully motivate you and help you understand why model-driven engineering is important and when we should really be considering applying it before we go deeper into technologies such as EMF and GMF and epsilon. So the way this first hour or hour and a half is going to be structured, we're going to talk about models in software engineering and in science in general. And in particular, we're going to distinguish between prescriptive and descriptive models. We're then going to introduce model-driven engineering, resolve any confusion that you may have behind this term, and talk a little bit about when it makes sense to use MDE and all that before we actually go and talking about MDE technologies. We're going to go through a few example MDE applications, talk a little bit about how MDE is being used in industry, and have a quick discussion about how MDE is related to low-code software engineering. So let's talk a little bit about models in science and engineering to start with. The word model is one of the most overloaded words in science. Some of you who are in the field of machine learning as well, you will already know that model in machine learning has a very special meaning. So we have things like UML models. So we have diagrams, but also in machine learning, a model means a very different thing. Now, if you talk to a biologist, they will tell you that it means yet another thing, or a mathematician, right? So we're going to talk about what a model is in the context of MDE. And so in general, in science, a model is an abstract description of a phenomenon or a system of interest. And models are made for a purpose. So a model is, by definition, an abstraction, which means that it has to omit details of the thing that it models. So again, by definition, a model doesn't really accurately capture all the dimensions of the problem or the system it refers to. However, models are useful. Despite being intentionally incomplete, they are useful. So we distinguish between two types of models, descriptive models and prescriptive models. Descriptive models are really abstractions of a system that already exists. And this can be a natural system, or this can be, for example, a legacy software system. The way we extract descriptive models is through observation, by running experiments and trying to kind of generalize behavior from what we see. Or through reverse engineering, where we get some sort of machinery to actually inspect the thing at close detail and extract a representation. And as I said, models are not entirely accurate, and this is intentional, but they are useful. So here what we have is a model of a hurricane, and you can see the areas with higher intensity and with the areas with lower intensity. And this is by definition not accurate, because the atmosphere is not a plane, right? It's not a flat surface, so we cannot say that at this point the pressure is such and such, right? So this is an abstraction. This doesn't capture the full kind of detail of the actual system, but still it's useful to know whether you should evacuate your house or not, right? Here we have the model of an atom, and we now know that atoms are not really kind of clusters of balls of like protons and neutrons, and then little marble balls kind of rotating around them. We know that things are much more complicated. So by definition, this model of an atom is wrong, right? But still, it can tell us whether two atoms will come together and form a bond, right? Based on how many electrons they have circulating in their outer orbit. To some extent, this also applies with models in model-driven engineering. When we model a system, we don't capture all its detail. We capture its useful detail for a particular purpose. So the reason why we why we construct descriptive models is to mainly understand how existing system works, unveil their inner workings, and also to generalize and make predictions about the future, right? So if we have such a model, we can then start making predictions about where this hurricane is going to go, or how quickly it will dissolve. And here, if we have models of different atoms, we can make predictions about whether they're going to stick together or where they're going to push each other apart. So these are descriptive models. We also have prescriptive models, and these are abstractions of a system that doesn't exist yet. And they define how that system should be implemented when it does. And in contrast to prescriptive models, which we extract by observation or by reverse engineering, descriptive models we have to construct manually, because they convey an inner, like an abstraction we have in our head about the system. We need to convey it to the rest of the world. So we need to construct, we need to transfer this mental model into something tangible that we can discuss, we can expose to other people. Why do we design, why do we make prescriptive models? So first of all, it makes sense to model when creating a model is cheaper and more flexible than building the actual system, right? And this is one of the main reasons why we draw models, because in a very cheap and flexible way, we can investigate different alternatives, alternative designs. So here, for example, when we're designing a house, we can design it in a certain way, and then we can look at it, and then we can decide, oh, you know what, I needed another bedroom, or I needed one less bedroom. And this is easy, this is cheap and flexible to change at the drawing level. It's not so easy if you've actually built the house, right? So this is an important property of models. They need to be cheap and flexible. So being able to investigate alternative designs and even reason about properties of the system in advance. So what we have here is a computerized model from a civil engineering toolkit that is used to design bridges. And this is not just a pretty picture, but we can also reason about the structural integrity of this bridge, about its ability to take a certain load without crashing. And we could even compute the bill of materials, so we could know how much steel and how many kind of nuts and bolts we need to construct this bridge. So models also help a lot with planning. They're not just about getting an impression about how the system is going to work, but they also help with more detailed planning. And planning is important because you can get into situations where you've developed the thing, and very late in the process you realize that it's wrong, it's incomplete, it's somehow broken in a way that is not easy to fix. Okay, so in model-driven engineering, we're not concerned too much about descriptive models, about models that describe systems that already exist. We are concerned with prescriptive models. And we can see models in three different forms, roughly speaking, in terms of fidelity. So when we're designing software, when we're writing software, usually this is a team sport, so we get a team of people to work together to do that. And before they start writing any code, they need to form a shared consensus, a shared understanding of the software that they're going to build. And this usually starts on the whiteboard. So you get everyone in a room or in a conference call, and then you start kind of doodling around and creating boxes and arrows and little clouds and whatnot. And these kind of models, which we call models, are sketches. They're very useful to facilitate informal discussion. So to develop that initial understanding of what we're setting out to build. Therefore, we don't use any particular notations or languages when we're designing such models. We're kind of free to create semantics on the fly and say, well, a cloud means something we're not very sure about, and a triangle means something that's very expensive, and a circle means something that only Tom can implement. We don't have to have fixed semantics for these models, and they are intentionally very, very incomplete, right? But still, they serve a purpose. They are a good communication tool. Then, higher up the fidelity spectrum, we have models as blueprints, and these aim to provide a more complete and detailed specification of the system. They are captured in languages with understood but kind of somehow flexible semantics. And in order to lead to software development, in order to lead to actual software, they require human interpretation and manual implementation. So you can get some designers that will design, for example, a class diagram of your ATM system, and they will define the entities like the ATM and the card reader and the session and the card and so on and so forth. And then they will design in detail what is going to happen when you enter a card into your card reader, that the ATM will create a session and so on and so forth. And then they will hand over these models to a team of developers who will then need to implement them in Java or .NET or TypeScript or you name it. So this is the second classification of models as blueprints. And finally, and this is the kind of models that we're going to be talking about in this MDE course, we have prescriptive models as programs. And models of this sort are precise enough to drive automated implementation of the system or verification of certain properties of the system. So we don't need the human in the middle who will take these blueprint models and will translate them into code. We'll add the missing detail that's required to convert them to code. The models of this sort have all the information they need in them to actually support the generation of fully functional code. And while here we can tolerate some flexibility because we have room for human interpretation, models as programs need to have very precise semantics. We need to be able to unambiguously say what each block and what each property of these elements exactly means. Such models tend to be captured in domain-specific languages just because they target specific application domains. And we will talk about domain-specific languages a lot during the rest of this course. So far, all these examples of models I've shown you are graphical, right? They are kind of edges and arrows and nodes and arrows and the like. But this doesn't have to be the case. And in fact, in model-driven engineering, there are many cases where you will find that your models are not really graphics, they can be text. So if you look at these two representations here, where we have a workflow, this is a model of a distributed application where we have some sort of source that feeds the application with input, in this case just pairs of numbers. And then we have components that can consume these jobs essentially and actually add the computation logic and then push the results on to another channel for a sink to actually consume. And this is a model of such a system. In reality, when we generate code and when we run the system, we have one source, we have one sink, but we can have a number of computational components distributed across different machines so that we can parallelize the execution of these programs. But this captures the essence of the system, so which component produces input, what kind of input it produces, what kind of processing goes on, although here we don't specify that adder really adds these two numbers, right? So this is a detail that we intentionally leave out of our model, and we'll talk about how we add this to our system. But if you look closely, this is exactly what this textual representation also says, that we have a workflow which has a certain source which produces number pairs to additions, and then we have a task called adder which produces numbers to addition results. So in terms of information, these two artifacts are exactly the same. They carry exactly the same information. And indeed, there are toolkits. There are tools in the MDE toolkit, and in particular in the Eclipse ecosystem that we're going to be talking about, where you can design your modeling language with a textual syntax, right? And equally, there are tools that you can use to create graphical syntaxes out of your languages. Now, in model-driven engineering, as I said, we use prescriptive models as programs, so we're interested in the higher end of the fidelity spectrum. And very often, we need to engineer domain-specific languages for capturing such models. And this is because of the precision that I mentioned before. We need our models to be very precise. We cannot really tolerate ambiguous concepts, which you kind of look and you get a feeling about what they mean, but you cannot really put your finger down and specify their exact behavior. And we also need supporting graphical and textual modeling tools. We also need to be able to express and check the validity of constraints for models. We need to be able to analyze and simulate models, because in model-driven engineering, models are like living artifacts. They drive the engineering process. They're not pretty pictures anymore. We need to be able to do meaningful things with them. And eventually, and perhaps more importantly, we need to be able to transform models into either other types of models or eventually software products, right? So we start with a model, we analyze it, we validate it, and so on and so forth. Eventually, the end game is to produce software. So when does it make sense to use model-driven engineering? Here I have two examples. This is by no means a kind of definitive list, but these are the two main reasons why you would get kind of a little bell ringing in your head that maybe I should be using a model-driven engineering here. And the first case is when you observe that the abstractions that your implementation technologies provide are not satisfactory, are not at a suitable level of abstraction. And you realize that when you see engineers needing to copy and paste similar boilerplate code and content again and again, and when, in order to make a change, they need to go and modify several interrelated artifacts in a similar way. So going back, for example, to the talk about ZapDev yesterday, if you have something like a business application that Katya demonstrated, and you have, say, a product table in your database, and you have some sort of product handling server-side logic, and you have a product form as well, and you need to change that, you need to add another field to the product, then in a regular development environment, you would need to go and change your database, and then you would need to change your form, and you will need to go and change your product processing logic. So to make one conceptual change, you need to go into at least three different places and change the code. And where there's a room for, or where there's a requirement for such kind of manual coordination, there is also a room for error, right? So someone might forget to change the database, or forget to change the form, or change things in an inconsistent way. And in any case, doing such work manually doesn't make sense. It's not productive. If anything, it can only introduce errors. So this is the first case where you need to start thinking, right, maybe the abstractions that I'm working with are not really suitable, and I need to be thinking about higher level abstractions from which I can then generate all of these artifacts in a consistent way. But model-driven engineering is not only about code generation. It's also worth thinking about models, and these formal models, when reasoning about properties of the system becomes too hard or expensive at the implementation level. And I have an example about that. So let's have a look at an example of the first case. Here we have a Java class that represents a customer, where this customer has an ID and the name, and we have some setters and getters, and then we have two methods, one that saves an instance of a customer into the database, and one that loads an instance of a customer by ID from that database. And this is code that you will find in any kind of ERP, any business application. You find lots of these beans that can persist themselves and read themselves from the database. And of course, there are frameworks that make this job easier. There are tools like Hibernate, etc., but they're not used everywhere, and even these tools add their own complexity to the code. Now, if you look very carefully, the only interesting information in this code is the fact that we have a customer that has an ID and the name. And if we know this information, we can write a little program that generates the rest. And not only that, but then it does the same for invoice and for product and for shipping order, right? So the essential information in this code is just this little bit, which we could express in the form of a class diagram or a similar kind of object-oriented modeling notation. And then here we are, generate the rest of the code. And then if at some point we decide that, well, you know what, we don't want to be using Java anymore, we want to switch to a different backend, then fine, the essential information remains the same. We can just write different templates and target a different programming language. That's absolutely fine. Of course, things are not so rosy in the real world, and we will get into details about the cases where you cannot really generate all of your code, but you can generate a lot of it, and you can write some of it, and how you coordinate this process and how you mix generated with handwritten code. So this is boilerplate code. This is a typical case where we would start thinking about models. The second example has to do with property analysis and verification, where we have cases where if we want to do any sort of automated reasoning about our system, it's really hard to do this at the code level. So here we have a switch statement that controls the change of colors in Christmas tree lights, because Christmas is coming. So what happens if the lights are blue, then the lights become red. If the lights are green, they become yellow, and so on and so forth, right? You wouldn't find this usually written in Java. You'd find it in a more low-level language. So what's wrong with this code? Right? It's not. No, you're not allowed to say. You've seen this before. So if you look at it for a few seconds, you will and you pay attention, and your brain is not frozen because it's like 0 degrees in here, then you will find out what it is. But if I show you a model-based representation of exactly the same information, you will see that there's no way we can get to the green color, to the green state, right? So already transforming a solution from a code to a model makes visual inspection easier. But what's more important is if we had, this is an example of a state machine, if we had thousands of states and very complicated transitions between them, we'd have no chance of detecting what's wrong, either manually or, visually, either in a graphical or in a textual representation. But when we've transformed our solution into a model, then we can use automated tools to actually check this for us. So, for example, do some reachability analysis. Okay, so these are two very common cases where you need to start thinking about applying model-driven engineering. The question is, how do you do that? So you know that you need to use model-driven engineering. For example, you're assigned to develop a new ERP product, right? How do you do that? Do you start drawing models? Do you start writing code? How do you approach it? Well, my view is that you cannot really model-driven engineer anything you don't understand, right? So the first step is never to start with models. The first step is to understand the system that you wish to build. And the best way to understand the system and the technologies is to build a small subset of it manually. So if I had to implement an ERP system in, I don't know, TypeScript and Node.js and so on and so forth, I know that eventually I would need to use models of some sort because there's going to be a lot of duplication there. But I'm not familiar with Node.js and TypeScript. So I would start with that end. And I would start with constructing a first small subset of my system using these technologies manually. And then as I'm starting to identify boilerplate and repeated code, I can start introducing models, and then I can start automating the development process. So a major decision that one needs to take when applying model-driven engineering is whether they're going to use an existing modeling language or whether they need to devise their own, and then based on that decision, or more or less intermingled with this decision, is how you want to process your models, because you may find that for existing languages you already have like auto code generation facilities or model reasoning facilities. If you had to implement your own language, you'd have to create your own. Which brings us into the topic of modeling languages. So there's no shortage of modeling languages out there. We have many of them. We have languages such as UML for object-oriented systems and Simulink for control systems, ER for modeling the schema of relational databases, and even languages for things like enterprise architecture and business modeling. And each of these languages focuses on a specific class of domains and specific class of problems. What you will find more often than not is that models, the kind of models you wish to construct to express solutions, to express designs for your domain of interest, are not really accommodated very well by existing languages. So the existing languages may be offering abstractions that are close to what you want, but really not quite what you want. And in this case, you have to think about defining domain-specific languages. And we're going to talk about technologies you can use to do that. But for now, I have 3 examples of kind of real-world situations, very kind of down-to-earth cases, where I will argue that existing languages are not really a good fit for what we want to do. So I'm going to talk about organizing conferences, designing collaborative projects, like the one we designed with the rest of the consortium to get Lowcomote funded. And in a more technical scenario, developing distributed data processing workflows. And I'm going to give you a live demo on that last one. So let's go to the first case. So suppose that you're asked to organize a conference, and that conference runs over a number of days. On every day, you have a number of tracks. And every track has several talks. And then you have breaks between tracks for things like lunch and coffee. And you need to allocate every track to happen in a particular room so that you don't get kind of 2 cohorts of people in the same room unintentionally. And you need to specify which talk is delivered by which speaker, and hopefully not get the same speaker deliver 2 talks at the same time in 2 different tracks. And you want to assign a duration to every talk. So what do you do with this information? You kind of get it all together, you assemble this information, and then you need to produce some artifacts to support the conference. What kind of artifacts do you need to produce? Some sort of conference booklet that you have to print and you have to distribute to your participants, which lists the different talks and the different tracks and when coffee is being served and so on and so forth. You would probably need a website that contains the same information but in a different format. So here you'd have something like a printable PDF or a printed PDF. Here you'd have HTML. You'd also want to print some track posters, so posters that you put outside of the room so that people who are just kind of hopelessly lost and just wandering around the conference can see what's going on in every room. You may also want to print name tags for your participants. You may want to print, for example, seat allocations for the dinner, and so on and so forth. And the challenge here is consistency and maintainability. So if you get a speaker to cancel their talk, or they get them to change to another track, then you have all of these artifacts. You have to change the booklet, you have to change the website, you have to change the possibly the poster track, and so on and so forth. And it's especially, if this happens in the last 12 hours before the conference starts, where everything is on fire, you're very likely to just miss one or more of them and to end up with inconsistent artifacts. Another challenge is correctness. So there are so many things that can go wrong. So you can, for some reason, you might end up putting the same speaker, as I said, giving 2 talks in 2 different rooms. You might get breaks that overlap with tracks. You might have a slot that is 60 minutes long, and you might assign by mistake 4 talks, 4 20-minute talks in that slot. And all of these things, if you're just working with Microsoft Word and PowerPoint and Excel, they will happily accept anything you type in. They will not complain, and you will only find out at the day of the conference. So there's a lot of information. There are kind of domain constraints that need to be satisfied, and there are artifacts, there are overlapping artifacts that need to be produced. So in a model-driven engineering environment, what we would do to simplify things would be to define a conference modeling language, right? And this is where I say that, well, there is a need for a domain-specific language. There's no such thing as a conference modeling language out there. There is UML, but that talks about classes and attributes and operations. There is, say, ER, but that talks about tables and columns. What we need to talk about in our models is participants, tracks, talks, breaks. So we need languages that have these concepts. And you won't find any, so you'd need to construct your own. Now, having constructed this language, we can capture all the information about a conference in one model, and then this model has enough information to generate all of these artifacts in a consistent way. So if we get a cancellation, or if we get an extra talk or an extra track, we just update our model, and then everything else gets generated automatically. Okay, so how do we go about designing research projects such as Lowcomote, or what do such research projects involve? First of all, they involve several partners, universities, companies, research institutes, like local administration. They have some sort of duration. So Lowcomote is 4 years long. Projects can be 3 years long, or 5 years long, or however much time you think you need to deliver the expected results. They are split into a number of work packages, like Lowcomote is. Every work package has a start and an end month, and it's broken down into tasks and deliverables. Tasks have a start date and an end date, and every deliverable is due in a specific month. And then every partner also declares how much effort they need, how much essentially budget they need for every task. So based on this information, we need to produce a number of tables in our proposal document. So we need to produce a table of deliverables by chronological order. So this comes from an actual European project where we see that we have a number of deliverables starting from month 3 and 4 and 6. And for every deliverable, we have the work package that produces it. It has an ID, a title, and a dissemination level that says whether it's public or restricted, and also whether it's a software or whether it's a report. This is one of the tables we need to put in the proposal document. We also need to put another table in there that summarizes the effort that goes into every work package, who is leading that work package, when it starts and when it ends. Now, for every work package, we have to have a more detailed table that says how much effort every partner in the work package is going to spend working on it, and what's the start date of the work package. Also here, if you notice, TOG is highlighted using bold font, which means that they lead this work package. Then we have another table, and these are all parts of the template, so they are compulsory. We're not masochists. We're not creating them just to make our life harder. Here we have another table where we have all the different partners and how much they contribute to the different work packages, and the totals for every partner. And then we have a Gantt chart, and these are only a few of the tables that we need to include in the proposal. And in the Gantt chart, we have the duration of each work package and the duration of each task in the work package, and the deliverables and their delivery dates, and so on and so forth, and also the different milestones of the project. So as you can imagine, it's very, very, very easy to get this wrong, right? To have a task that, for example, outlives its work package. So it would be fine to have a task that kind of goes into month 7 here. If we were just using Word, it wouldn't care. It would happily let us do that. Or, for example, we could have deliverables that are outside of the scope of a work package, or we could have work packages that could extend after the end of the project. There are all sorts of things that can go wrong. We could have the work package leader having no effort in a work package. And if you think these are kind of unlikely things to happen, again, 12 hours before the deadline, everyone is in panic, things changing the whole time. It's very easy to get inconsistencies in there. So again, what can we do? We can use model-driven engineering, and we are using model-driven engineering in order to develop these kind of big grant proposals, where we're capturing the essential information about a project in the form of a model that conforms to a research project modeling language that has concepts like task and work package and deliverable and partner and effort and so on and so forth. And then we produce all of these tables, all of this content in an automated fashion, and we know that it's going to be correct by construction, right? So we don't even need to go and check the sums or anything. So none of these two examples that I've shown you so far has to do with code, right? And the topic of Lowcomote is low-code software engineering. But you hopefully get the picture already. There's no difference in generating LaTeX code or HTML code or Java code. All of them are just textual artifacts. So the process and the rationale is very similar. But let's actually have a look at an example that involves some code. And this example has to do with distributed data processing workflows. So these are applications that distribute the processing of streams of data across multiple computers so that we can achieve horizontal scalability. This work was triggered in the context of the Cross-Minor European project. This is another Horizon 2020 project that we are involved in, where we had to analyze large volumes of open source software repositories and knowledge bases, things like GitHub and Stack Overflow, right? And in particular, the kind of applications we wanted to be able to write was like this. So, for example, here we have certain technologies that we are interested in. In this case, we have XML parsing libraries in Java. And for every technology, we know its name. We know one of the keywords that we should expect to find in files that make use of that technology. The extension of files that refer to this technology, and a hashtag, a Stack Overflow hashtag for that technology. And we can have a number of them. And what we want to do is we want to assess how these, the extent, the popularity of these different technologies across GitHub and Stack Overflow. Because if we have several technologies that we're considering as alternatives, going with one that's very popular is kind of always a good heuristic. So what we want to do is we want to take these the technology descriptors, have one component that goes to GitHub and it searches GitHub and it collects the number of repositories that make use of this technology, and we want another component that goes to Stack Overflow and collects the number of posts that refer to this technology. So if we know how many posts refer to this technology and how many GitHub repositories refer to it, then we can have a pretty good estimation about how popular it is, and then maybe we can choose the most popular of these technologies. So if we want to do this for a large number of technologies, there's no reason why we should be restrained in one machine. If we have a cluster of machines, we can distribute, we can send different technology descriptors to different machines that can individually query Stack Overflow and GitHub, and then we can collect all of these results. Also, if we've done this work for a given set of technologies, and then we add one more, right? We would like our solution to cast the results computed in previous runs and only go and check the last technology, right? Because in this case, we don't care about very timely results. It's fine if we get like 5 minutes old results. So how do we do this? How do we develop such applications? We have developed a language called Crossflow, which is a distributed data processing language. So we can define these workflows in terms of models, and then we can generate from these code that does all the uninteresting bits, all the scheduling and the caching and the communication between different nodes. And then we only need to go in and say what this task does and what this task does. So given this technology description, how do we count the number of GitHub repositories? That's not something we do in the model. That's something we do in code, but in a very controlled way. So I'll just give you a demo, show you how that works. Which are the files? Okay, so what we have here is, let's have a look at our language, first of all. So this is our domain-specific language, which is called the Crossflow, and it's implemented using eCore, which is the meta-modeling technology we will cover in this course. So that just gives you a preview about the concepts of a preview of eCore, and just a quick overview of the concepts that our domain-specific language contains. We have things like workflows and streams and tasks and types and fields, right? And here we have a model. This is a textual model with a generated graphical representation that defines the name of a workflow. It defines its source and what kind of stuff it produces. In this case, it produces number pairs to this additions queue. And then we have a task that consumes from the additions queue and is called adder down here, and it produces numbers to addition results, which is another stream here. And then we have our sink, which is called addition result sink, which consumes the outcome of this queue. And you'll see that this is a generated representation, a generated graphical representation of this mode. I'm changing the name of the sink, and you can see how that node changes here. And here we have the two types, the two data types involved in our workflow: number pair, which has two fields, A and B of type int, and number, which has a field n of type int. So this is the simplest possible workflow you can create in this language. Essentially, you get pairs of numbers, you add them up, you produce a result here. So the only thing we need to implement to make this a running application is the actual logic of this one, of adder. What it does with this pair of numbers and how it transforms it into a single number. So we have a code generator built on top of this crossflow language. So from this model, what we get is all this generated code. And here you will see, let's go back to our diagram. Here you can see that we have a generated class for every type, number pair and number here. We have a generated class for every stream, so additions and addition results, right? And if you look at these classes, they use a messaging middleware called Apache ActiveMQ, which enables asynchronous communication between components, right? This is code that's all generated. This is code that you don't, as a developer, have to worry about because it's correct by construction to the degree to which our generator is correct. What you need to do is two things. So this is the source gen folder of our project. This is where all the generated code goes. There's also a source folder where the only thing you would need to do as a developer is to define what adder does, so the behavior of adder, the behavior of the source, and the behavior of the sink. Right? And everything else, all the communication, all the distribution is taken care of for you. Let's have a look at adder. So from our model, we generate this adder base class. And this has a lot of code in here. The one thing that it doesn't know how to do is to consume from this stream here. So it doesn't know what to do when it actually receives a number pair. And this is what we need to specify using Java. This is what our language does not capture. It doesn't capture behavior, it only captures structure. So what we need to do is we need to create a subclass of this generated class where we go and implement this consume additions method. And if I get rid of all the stuff that I've put here for debugging reasons, this is what we need to do. So we need to say that the result of this task is another number, and we're going to set its n property to the sum of the A and the B of the incoming number pair, and we're just returning it, right? And then the framework, the generated code, will take care of all the rest because we can run these. We can run several instances of this workflow across different machines, and they will talk to each other, and they will distribute number pairs and collect numbers. But as a developer, we don't need to know anything about that, right? Okay, I will restore this code because otherwise it's going to complain when I try to run it. How do we run this? What's the simplest example? Yes, okay. So then we can instantiate a workflow. We can set the number pairs in its number pair source, and we can set some sort of termination timeout, and then we can run the workflow, and we can assess that what has been collected in the sink is what we are expecting. So there's lots of code here that we didn't write, because remember the only code we had to write was this bit over here, plus a little bit of code that says how we feed the workflow with numbers. So the generated class for the source has a produce method where we need to kind of read from whatever is our real source, which might be a database or a spreadsheet, and then we need to send input to the additions stream, which is the first stream of our application. Okay, so that hopefully gives you a first flavor of what a domain-specific language and what a generator that produces kind of executable code looks like. Okay, so is model-driven engineering a silver bullet? Can you use it everywhere? The answer is, of course, no. There are certain things you need to look out for. One of them is return of investment, because developing domain-specific languages and developing code generators is no easy task. There's a lot of thought that needs to go into that, and probably a lot of development time as well. And that initial return of investment may take a little bit of time to pay off. So in some cases, it will not pay off the first time you use your generator for the first system you develop, but it will pay off over time. So if you're just developing a one-off system of a limited scope, then maybe that initial investment will kind of never pay off. And this is why product lines are often a very good fit for MDE. So you tend to find MDE implemented in companies that develop kind of variants of the same system or very similar systems all the time, right? So, for example, aircraft engine manufacturers, they have several models of essentially the same core with some features added, some features changed, some features tuned to different values, right? And they tend to use a lot these sort of technologies. Another thing to look out for is what we call scope creep. So when you have a language, when you have your own domain-specific language, it's easy to start kind of extending its scope and thinking, oh, in this workflow modeling language, why am I only capturing structure? Wouldn't it be nice to also have the behavior in my model? So then you start introducing classes such as if statement and for statement and variable declaration statement, and eventually you end up with a poorly developed programming language, right? You don't want to do that. You want to think about what is the best part of the system to capture using a model, and what is the best part of the system to capture using just straight code. And there are some parts of the system that are really best captured using code. We don't have to model everything. We don't have to model for the sake of modeling. Okay, so I had a few slides here, but I've shown you, we've gone through these yesterday. These are some examples of companies that make use of model-driven engineering technologies. This is from the latest Models conference in Munich in October. So these are fairly recent talks. Now, as with everything that matters, MDE has been involved in its own hype cycle. So it's not a new concept. It's not something that we came up with over the last couple of years. It has been around since the early 2000s, and it has gone through this. So this actually applies. This is a generic graph that applies to any technologies. You can put machine learning here. You can put blockchains here. You can put kind of self-driving cars here, and all of them are kind of in a different part of this slope, right? So I think machine learning is somewhere over here right now, and you can see what follows. I'd say that model-driven engineering is somewhere here. There was a lot of work went into in the early 2000s. It was oversold spectacularly, right? It was meant to be the silver bullet that will just fix the world's problems. Then at some point, people realized that actually, it's not. And then we've started climbing out of this trough and finding out what is useful about MDE, where we should use it, where we should not use it, what kind of tools scale up, and so on and so forth. So now we are entering this plateau of productivity where we don't have inflated expectations. We know what it's good for and when we should use it and when we should not use it. Now, in terms of tools, just very briefly, there are all sorts of tools that enable model-driven engineering. We have commercial tools with code generation capabilities, things like IBM Rhapsody and Magic Draw and PTC Integrity Modeler. These are more appealing to companies that are not really interested too much in developing their own domain-specific languages. UML provides some customization capabilities in the form of UML profiles, which is a mechanism that you can use to extend concepts that UML already provides with additional properties. MATLAB Simulink is very, very popular for model-driven engineering, and they are expanding their tool set. So now they have a requirements modeling tool, and they're building an architectural modeling tool as well. They're very widely used in the safety critical systems industry. You have toolkits like SCADE. And then on the more kind of domain-specific languages end, we have the Eclipse modeling ecosystem, which is what we're going to cover in this course. So these are all open source tools for domain-specific language engineering and for developing all the rest of the tools that go with domain-specific languages. And then JetBrains MPS. You may be familiar with JetBrains from IntelliJ, the developers of IntelliJ. They have their own metaprogramming system, which offers projectional editing capabilities. We will talk a little bit about MPS later in the week. So the take-home message here is that there are several different tools that enable model-driven engineering. It's not just going to be, it's not just EMF and the Eclipse modeling ecosystem. There are many commercial alternatives. I should have mentioned here MetaEdit Plus, which is a domain-specific modeling workbench with a very long and successful history in the past. So yes, it's not just EMF. We will be covering this part of the tool ecosystem, but there are many, many other options as well. Now, how is model-driven engineering and low-code software engineering related, right? Why do we teach you model-driven engineering while your training network is on low-code? So low-code software engineering platforms make use of all these MDE techniques. They use domain-specific languages, they use code generation, they use automated model transformation and model checking to deliver full-stack applications on top of proven architectures. So if you like it, MDEs are the techniques, and low-code engineering platforms are what kind of package these techniques and offer them to users for the development of ready-to-use applications. Why low-code? Why has it emerged now? I think it's a... So what has enabled low-code engineering platforms is the advance of cloud computing and containers and so on and so forth, which now makes it easy to actually run a generated application with very little configuration. So most of the model-driven engineering techniques you will find in the literature, they start with a language, they generate some code, and then they just hand you over the code. And that's it. You have to then run it, you have to deploy it, you have to manage users, credentials, stuff like that. A low-code platform will generate the code, but it will also run it for you. It will also instantiate the database. It will have built-in reusable, like user credential management functions, and so on and so forth. And actually, there are several of these. We have talked about ZapDev and Quid yesterday, but there are also things like Microsoft Power Apps and Google's App Maker, and companies such as Salesforce and Mendix and OutSystems. Very, very many low-code systems, and the number is growing as Pedro demonstrated yesterday. Okay, so I think that's it for this first hour. We talked about models in science and engineering, about prescriptive and descriptive models. We talked about model-driven engineering itself, and what it means and when it makes sense to use it. We've talked about these sample MDE applications, organizing conferences, writing grant proposals, and then developing distributed data processing applications. And then we talked a little bit about how MDE and low code are related to each other. So let's now take a break for 10 minutes, and we'll come back with a presentation of EMF. Any questions before we break? Yes?
So is the code generation a part of MDE, or it can be used otherwise?
Yes. Yes, code generation is a very common technique used in MDE.
Okay. So because I've seen a low-code platform named OutSystem.
Yes?
So it used it mentioned that it used code generation technique.
Mm-hmm. Yes.
And in other parts like Zoho Creator and like Power Apps, they have mentioned they used MDE. So it's just name difference? Or
Yes, it's a matter of terminology. The techniques are the same. You start with some sort of model, regardless of how you express that, how you present it to the user. It might be in a text or syntax in the form of kind of a drag and drop form, a diagram, and then you generate code either visibly or behind the scenes, because that is what the application, the final application, consists of. Yes?
You mentioned in MDE the code is generated automatically, but some parts of it, in some parts it should be manually.
Yes.
If the models are very huge and we deal with larger scale models,
Mm-hmm.
how can we show that the manual part of the code is complete? And
Complete with reference to what?
which reference to every part of the model is generated, whether automatically or manually.
Mm-hmm.
How can we deal with larger scale models? Because different parts of it should be generated manually.
I mean, there are ways to manage incomplete code. So, for example, what I showed here with the data processing application generation for every task in our model, and it could be a very large model, we generate an abstract class which has a method that's not implemented. In order to make that code executable, we need to implement concrete subclasses for all these abstract classes and implement these methods. If we don't, we get compilation errors in our IDE.
In the model that you showed, the adder should be generated manually. So if we have a lot of parts of the model, they are separated in different parts of the model. That should be manually. How can we show that the developer doesn't forget?
Sure. Okay. So let's go back to Eclipse. So in this particular case, you'd say what would happen if I had forgotten to implement the logic for adder, right? So you see I get compilation errors in my generated code here, right? So that won't let me run my application. If we look at the compilation error here, it will say that I expect a class adder, which you haven't defined. So I will complain until you actually do that, right?
The other class will be the complete one.
Exactly. Yes. Okay. And there are other ways to do.
For example, sorry.
No. Go ahead.
Well, for example, I make two implementations to have an alternative. There's some way to specify which alternative to run, or I just can have one alternative?
You can have one alternative that your code knows about, but of course you could then in that class you could delegate to two different alternatives based on a condition or whatever.
Okay.
Yeah. Or there are other ways. We could generate a default implementation of other that has a to-do item. There, a to-do Javadoc item, and then you will get in your problem in your in your problems you will get an information item saying, well, you have this thing that you need to implement.
And you showed that the model is synced with the generated code.
Yes.
And is the debugger synced also? For example, we saw that something is missing in the code. Is it possible to show in the model too that this part of the model is missing in the code?
So in this case, nothing is missing from the model, right? We're just missing an implementation. Yes, I mean it is possible to do that. You would need to effectively look at the generated code and look at the problems, at the compilation problems it produces, and then use the traceability information from your model to text transformation to backpropagate these to your models. This is not something that we commonly do, but it is technically possible, yes. Any more questions? Okay, let's break for 10 minutes and we'll come back with EMF. We're going to talk about the Eclipse modeling framework, which is really the foundational technology of the Eclipse modeling ecosystem. We're going to talk about its meta-modeling language, which is called eCore, and we're going to see how we can create meta-models or domain-specific languages using eCore. And then, because we don't meta-model for the sake of meta-modeling, we will also talk about how we can instantiate eCore-based domain-specific languages and create models that conform to them. And we're going to do this through a reflective editor that ships with EMF, but also through some tooling that EMF provides for generating custom tree-based editors for eCore languages. And in the next lecture, we're then going to see how we can create graphical editors for our eCore domain-specific languages. So a little bit of history. EMF has been around since around 2002. It started as an internal product at IBM. Several IBM tools had the need for domain models for defining and then serializing domain models. And out of this need came EMF. It is used in several commercial products, things like IBM Rational Software, or BioDesigner. So these are all tools based on top of EMF. EMF is used under the hood in a very large number of other tools as well, which don't expose it but kind of use it as their core. And it is the de facto standard for modeling in the Java world, and as I said, it's the basis for the Eclipse modeling ecosystem. So there's a wealth of tools that build on top of EMF. So EMF provides a dedicated object-oriented meta-modeling language called eCore. It provides tools for creating eCore models, but also for creating models that conform to eCore based languages. It provides support for serializing and deserializing models, so it supports the XMI standard, but it also has a pluggable architecture that can be used to implement different ways of persisting models. And for example, there are tools like Xtext where you can define textual syntaxes for your models, and they will be persisted as what you would recognize as code files. Essentially, there are tools like CDO where you can persist your models in relational databases, tools like NeoEMF where you can persist EMF models in Neo4j databases and graph databases. And this is all thanks to this pluggable model persistence mechanism that EMF supports. And then it also provides a built-in model validation framework where we can hook in constraint languages such as OCL and EVL, which we'll talk about later in this course, to implement validation constraints, so to check properties that eCore itself cannot check. By default, models in EMF are persisted using XMI. XMI is a standard managed by the object management group. Essentially, it's XML with identities. Because models are essentially typed object graphs, we need to be able to refer between elements. XML, by default, is a tree, so we need a tree with ways to cross-reference other elements, so essentially identities, and that's what XMI is pretty much. Okay, so we will use a domain-specific language throughout this, this lecture, and this language is focused on call center applications. So suppose that you find yourself in the business of writing software for call centers, God forbid. You will find that you will need to design several kind of call center software for different customers. If I zoom into that, this is one example of the kind of call center software you may have to write for a customer, where you start with some sort of greeting. So you call into a number as a customer, you're kind of greeted by the system, and then you're asked the question, are you an existing customer? If you answer yes, then you're asked to enter your account number. And then you're asked to enter your e-banking PIN, and if that gets validated, then you're just notified that the call may be recorded, and then you're asked to select one of the following options for mortgages or for savings accounts, and depending on what you choose, on what you speak out, you get redirected to a different number in the company, right? So this is software that you would need to kind of sit down and type in Java. I think that having such a representation of the call center software is much more reasonable. It's much better because that is something you can talk about with business experts. You cannot really show them the Java code; they won't understand much. But if you show them a model like this, then you have a chance of getting feedback, of maybe deciding that, well, this menu is too long, it has too many options, maybe we could break it down in this way or that way. And then once you have all this information in your model, you can code generate, you can produce the code that implements that system automatically and consistently. So first step is we need a language. We need to be able to express such models. And we're going to construct such a language using EMF. Okay. So this is an instance of Eclipse, like the one you have downloaded and you have installed in your computers. And it's a clean workspace, so nothing here. We'll start by creating an empty project.
Should we follow along?
It's up to you. You will have time to do all of that in the practical in the afternoon, but if you prefer to try to follow along. I try not to give live demos where students try to follow, because then if someone falls behind, we need to interrupt the lecture, need to go help them, and so on and so forth. So it's better if you just maybe take some notes, and then you can repeat this in the afternoon. Okay, so what I'm doing is I'm creating a new project, and I'll give it a name. This is the project where I will have my language. So I will call this the flowchart project. And that's it, really. It is just a folder at this stage. And I will create my meta model. So I'm going to use a notation called emphatic, which is a textual syntax for eCore, so that I don't have to point and click too much, but instead I can type in my meta model. I will create a language called flowchart.emf. And I'll just grow the font. So in EMF, EMF uses the term package for meta model. So when I use the term package, meta model, domain-specific language, in terms of EMF, it's all the same, right? So I will create a package called flowchart. every meta model in EMF needs to have a unique identifier, a globally unique identifier that no other meta model has. So EMF calls this property a namespace URI, and I'm going to type in a URI here. Usually you will find that URIs look like URLs because they have to be globally unique. So if I really wanted to make this globally unique, I would say something like, okay, and this is my domain name, so I know that this is globally unique, or it should be globally unique. To avoid some typing, we'll just leave this as flowchart for now. And then for the persistence reasons, we need to define this prefix property as well, but that's not important. Okay, so this is our meta model. eCore is an object-oriented language, which means that we will express the contents of our meta model in the form of classes and relationships between them. So classes are going to map concepts in our problem domain. So if we look at our sample model here, what concepts can we see? We can see actions, right? So we'll start with a class called action. This is something that the system does. Okay, what else can we see? We also have decisions here. So here is where the user needs to make a decision. Okay. We also have actions have some sort of text, right? Here. So we can add an attribute to our action class and say that, well, this has an attribute of type string, which is called text. Now, if we look at decisions also have a text. They have a question, right? So could go here and say, well, this also has a text. Now, if we start thinking about, well, what we're not representing here is these arrows, right? And we will call these transitions. And we can have transitions from actions to decisions, from decisions to actions, and so on and so forth. For now, we'll just define a class called transition. Okay. And we would need to specify references for this transition, so where it comes from and where it goes to. Now, it can come from an action and it can go to a decision. It can come from a decision and go to action. We can also see that action and decision have this shared property, so this all smells like a need for inheritance, right? So we will create an abstract class step, which will have a text, and then we will make action and decision extend step. Okay, and the reason why we made step abstract is because we cannot really instantiate steps. We can either have actions or decisions. We cannot just have steps. So having done that, our life becomes a little bit easier with transition. So a transition has a reference to one's step, which is called from, and it has a reference to another step, which is called to. Okay, good. So what else do we have here? If you look closely, you can see that there are two types of actions. There are things that the system will tell the user, like welcome to this bank, or be aware that the call may be recorded. But there are also actions where the system expects some sort of input. So here it expects an account number, here it expects a PIN number. So these are not really exactly the same. Also, there's a third type of action where the system actually calls a number for you. When you reach that action, it actually calls a number. And you can see that because these two have the same label, so they just redirect to some number. So what we can do to accommodate this in our language is we can add further subclasses of action. So we can have a class speak action, which extends action, and we can have another class called redirect action, and in redirect we'll also need to specify the phone number where the call will be redirected, so that we're consistent with what's happening here. And the phone is not an integer, so I'll represent this as a string. Okay, and we also have some sort of input action. If we look at here, these two would be input actions because they start with like, please enter something. And here we would have, so this also extends action. And here we have the variable that we expect the user to populate. Okay, so these are all the concepts that we need for our domain-specific language, right? It doesn't look like a programming language. We don't have it's not a Turing complete language. We cannot have for loops and functions and stuff like that. We can just have actions and transitions and decisions and so on and so forth. So, good. Now what we're missing here is some sort of root concept where everything else can be contained. And this is important for some tools that work with EMF. We need to have some sort of root class, which we normally call model, where we can contain everything else transitively under. So a model would have a number of steps, and it would have a number of transitions, and then that's about it. So here you can see, I'll just move this to the top. So here you can see that we have two types of references in EMF. We have containment references and non-containment references. Containment references are represented using the val keyword in emphatic, and the semantics is that if we delete the container object, then all the contained objects get deleted as well. So if we delete a model, all its steps and transitions disappear with it. Non-containment references, such as this one, don't carry this semantics. So this means that if we delete a transition, the two steps that it refers to, nothing happens to them, right? They don't get deleted. Okay? This is the semantics of containment and non-containment references in EMF. What else? Yes, okay, so I think that is sufficient for now. So as I said, emphatic is a convenience textual notation for typing in E-core meta models. In order to do anything useful with these meta models, to instantiate them, etc., we need to transform them to E-core. So if we right click on our emphatic file, there's a generate E-core model option here that will produce an E-core meta model. So this is the same information, but in a different representation that that the rest of EMF can work with. So we can see how we have a model that has steps and transitions have a from and to, all the things we implemented using emphatic. Now, now we need to be able to instantiate our meta model to create a flowchart model like the one. I just need to close this. To create a flowchart model capturing the same information that we have in this diagram. It won't be a diagram. It will be using a basic tree-based editor, right? But the information will be exactly the same. And tomorrow we're going to talk about how you can create a graphical editor that looks like this. So, in order for EMF to be able to instantiate a meta model, it needs to know about it, right? Right now, this ecore file is just a file sitting in our Eclipse workspace. EMF does not monitor your workspace. It doesn't know which meta models, which of your files are meta models and what it should do with it. So you have to be explicit about this. And you can right-click and say, well, register the packages of this meta model. And now EMF knows about your meta model, which means that then we can use this new EMF model wizard, right, under epsilon to instantiate our meta model. And let's call this bank.model. The URI of the meta model it needs to conform to is flowchart, is whatever we typed in the first line of our emphatic meta model. And then the root instance type, here we can see all the different types we specified in our meta model, but not step. Because remember, step is an abstract class, we cannot directly instantiate it. So we'll go with model. Okay, so now we can right-click and go new child. Okay, that's interesting, because I should have made action abstract as well. We can create speak actions, and we can create input actions and redirect, but not actions per se. That's fine. So I'll go here and say, well, you know what, action is abstract. The other way around. Okay, so I'll need to regenerate my meta model, register it again, open my model, so new child. You can see how action has disappeared from here. Good, so let's start creating the model. So we start with a speak action. Its text is welcome to Evil Bank. If we look at our diagram, then we need to create a decision. New child, decision. Are you an existing customer? Now we need to create a transition that links the two. So right-click again, new child, transition. Our from is this speak action. Come on. Yes, and our to is this decision. Okay, and we can go on like this, and we can reproduce the rest of our model. We could create a new, say, redirect action, and here you can see that we have two properties. We have the text, but we also have the number, because redirect action extends action, and therefore step. So it has a text property, and then it also has this number property. So if we go here, we can see these two properties here. Okay, so yes, we can follow the same process, and we can create instances of the rest of the types, and we can capture all the information we need about our model. What is another interesting feature of EMF and emphatic is its support for opposite references. So here we have specified that the transition goes from one step to another. We can also specify that a step has a number of outgoing transitions and a number of incoming transitions, right? And this can prove useful when we are then writing model validators and code generators, etc. We may want to be able to navigate both from steps to transitions and from transitions to steps, right? Now the problem in the current way I've expressed these properties is that they are not synchronized with each other. So if I was to leave it like that, I can right click, generate my core model again. So here you can see we also have these incoming and outgoing references. And here you would expect that because this transition goes out of this speak action, it would also appear in the outgoing transitions of the action. But it doesn't. Because if you look at these properties, there's nothing that says that they are linked in some way. Yes, they have opposite types, but that's fine. There's nothing that says that from should be opposite to outgoing and to should be opposite to incoming and not, for example, the other way around. Well, EMF supports specifying opposite references, so we can actually declare that from is opposite to outgoing. And we need to specify it on both ends. And we can specify that to is opposite to incoming. Okay, and we specify this on both ends of the association. So now
it automatically knows that it's a one-to-many.
This is many.
Yeah, so it automatically knows that because one is an array and the other is a singular array.
We can have opposites between one-to-one, one-to-many, or many-to-many. Yeah. And then it will synchronize them on its own. So in this case, we have a one-to-many relationship, right? Both of these are one-to-many. So if we generate our eCore model again, it will automatically register the new version. Now, if we go here, okay, right. So if I go and change the action to welcome and then change the target to decision, then you can see how this transition has now appeared to the outgoing transitions of the speak action, and it has appeared in the incoming transitions of the decision. Right? So using opposite references, we can essentially link references, pairs of references together so that when we change the one end of the reference, the other end gets updated automatically. Okay. Yeah. eCore also supports enumerations. So for example, we could have an enumeration called voice, and it could be male or female, and then we could say that in the different steps we also have an attribute of type voice, where we specify if the text will be spoken out by a male sounding voice or by a female sounding voice. Okay, so you can see that enumerations are captured using attributes within classes, and they have this special syntax to declare the different options they provide. So I will generate the model again. And now here we can choose male or female in every step. And we get the first value of the enumeration as a default value. Okay, what else? So compared to Java, so you will have noticed that emphatic looks a lot like Java, and that's no surprise because eCore is implemented in Java and the whole technology stack is implemented on top of Java. One difference between eCore and Java is that eCore supports multiple inheritance. So you can have classes extending more than one classes, which is not permitted in Java. Talked about references. We've talked about opposites. Another thing one can implement and define in emphatic is operations. But we can only define the signature of an operation, not its body. If we wanted to define the body of the operation, we would have to modify the generated Java code very similarly to what we did in the previous example. I won't go into that because using languages like OCL and EOL, we almost never have to do that. We can implement operations for our meta models using interpreted languages on top of them. Okay, so this is pretty much how we define a meta model and how we can register it and how we can then instantiate it. Now, so far, I've been working in the context of a single workspace. So I have my meta model and my model in the same workspace, in the same Eclipse workspace. The editor I'm using ships with EMF, and it has some basic functionality. But for example, if I wanted to change this icon, or if I wanted to change this label to be a computation of some other properties of the of my domain object, that's not possible because that's the editor. It's reflective. It's kind of end of story. EMF supports generating editors, generating dedicated editors from languages too. So I can go to new, other EMF generator model, and that will create another model with the same name but a .gen model suffix. From which I can generate a dedicated tree editor for my language. So this will now generate lots of Java code. You can see that we started with one project, and now we have this flowchart.edit and flowchart.editor and flowchart.tests project. And here, what has actually been generated, let me change to the Java perspective. So in the generated source of our flowchart project, you can see that we have one interface for every class we defined in the meta model. And then we also have one implementation class for every class defined in the meta model. And we also have some utility classes and so on and so forth. And we can go and change the generated code, and EMF provides a way to preserve changes to our generated code. So let me show you how this is done. Say, suppose that we wanted to have an operation here called, no, actually let's go to step, and suppose that we wanted to have an action, an operation which is called get next, and which returns a step, because actions can only have one outgoing transition, so you might want to implement a convenience get next operation that will just get you the next step. Okay, so this is my emphatic. I can generate my E-core again and reload the generator model. So update my generator model because I've made changes to the E-core meta model, and then generate all again. Okay. So if we go to a model, to our action class, there should be this get next operation, which has been generated from this signature over here, but it doesn't have an implementation. So by default, it will just throw an unsupported operation exception in Java. What we can do is we can go in and implement it and say if this dot get outgoing dot size is greater than 0. So if there is an outgoing connection, then return this get outgoing dot else return null. And now we have to instruct EMF to not override this code the next time we run our code generator, because we may make more changes to the meta model, we may want to rerun the generator, we don't want EMF to lose this code. So EMF's way of doing this is by changing this annotation here in the code and saying that this is not generated content anymore. So the next time EMF will run its code generator, it will not overwrite this file, but it will merge it. It will merge the new contents with whatever it finds in a non-generated method here. We'll come back to this technique. This is only one of the available techniques to integrate generated and non-generated code. Okay, so we've generated our code. This has also generated beyond the domain model, beyond classes for a model, it has also generated a dedicated editor in the form of an Eclipse plugin. So in order to run this editor, we will need to run a new instance of Eclipse that contains everything that this instance contains, plus all the code we have here. All the extensions that we have here. So to do that, we can right-click on any one of these projects and say run as Eclipse application, and that will launch a new instance of Eclipse that contains whatever our base workbench contains, plus these generated plugins. Okay. So I'll get rid of this. So here, this is a new instance of Eclipse where our tree-based editor for the flowchart language is operational. So I will create a new project like before. I will call it Evil Bank. And then I will right-click and say New, Other. And here you can see how we have a new flowchart model entry. This comes from the generated code in the previous workspace. So a new flowchart model. Yes, I will need to go. I messed up my Java installation. So I will need to go and change the compatibility. Yes. Okay, so the model object like before is going to be model. And here you can see how we have a dedicated file extension for our models. And we have the same functionality, but because it's generated content now, we can go into our generated code, and we can customize the look and feel of this editor. We can replace these icons. We can change how these labels look like. We can add more context menus, and so on and so forth. Now, if we look at the model, using a text editor, this is XMI. So here we have an XML representation of our model. We have this model, top level element. We have 3 steps with different types, speak, action, decision, and redirect action. This says that these 3 objects go into the steps reference. If you remember our meta model. So model has steps. Every object has an ID, and that's an auto-generated unique ID, so that objects can refer to each other. For example, here, this transition refers to 2 steps. This one, if we look at search, that's really the speak action, and then 2 is the ID of our decision, and then we have the extra properties, text, and a number when we're talking about redirect actions. So, in the worst case, if you do something terrible to your meta model and you have a model that you've already created and the model breaks, for example, I could go here and say, well, I don't like the name transition anymore. I will call this link. Okay, so I'll need to go and rename this. And I will generate my eCore again. Now, if I try to open my model, well, the text editor will always open it. But if I try to open it using Exceed, well, in this case, it's smart enough to tell that to tell what I've changed. If I make things a little bit more difficult for it, so I'll change this to source and target, and this the source and target. And I'll generate my equal model again. I'll try to open my, and now it complains, right? Because I've changed my meta model. My model is still refers to from and to and so on and so forth. But the good thing is that it's a text-based notation, so I can always open it with a text editor and say, well, okay, this is not transitions. This is, have I changed the name of the reference? I probably haven't. It's still called transitions, which is why the first change did not break. But here I can go and say, well, this is actually source, and this is target, and then I can open it again with my tree-based editor, and everything's fine, right? So it's that. This is the nice thing about a text-based format. You can always resort to the text editor if you have to. You shouldn't have to do that too often, but at least it remains an option when you need to do that. Okay, so we've talked about generating code and how to run your generated editor. We've talked about operations. So there are a couple of other options for creating eCore meta models. There is, for example, a graphical editor. There's a there's an editor that makes your meta model look like a class diagram in UML, and you can draw your classes and link them up instead of typing them in. I personally prefer typing to pointing and clicking. And then there are two alternative textual syntaxes, very similar to emphatic. One is called OCL in eCore, and it supports also defining the implementation of operations using a language called OCL. And then there's Xcore, which is very similar, but it uses a different expression language for defining the implementation of operations. It's really a matter of preference. Any of the three languages would do. Mm-hmm.
So those other languages, like the graphical one, do they provide also the text version, so that maybe if you want to edit, you can edit it?
The interchange point is your .ecore file. So you can create from emphatic, you can create your eCore file. From your eCore file, you can create a diagram. From the diagram, you can change your eCore file, right? So there are bridges between these different notations. My advice would be to just choose your preferred one and stick with it. So sometimes you need to produce diagrams for your meta models, just for kind of documentation purposes. I tend to do all my work in emphatic, and then when I need to generate a diagram, I use the diagrammatic tool to just create a diagram, lay it out, put a screenshot in a document, and forget about it. Right? Come back to it next time I need the screenshot, really. But that's me. Okay, any questions? Yes.
In our real-world example, the bank, there's a sense of sequence. For example, the welcome message is first.
Yes.
That is not explicitly encoded in our model. Is it the role of the generator to do that, or?
It is, in the sense that this speak action is the only action without any incoming transitions. So in a graph, it would be the source of a graph, essentially.
So it's implicit.
It's not. It's very explicit, because the way you can tell, if you look at our model, the way you can tell that this is first is because it's the only one that doesn't have an incoming transition. And that's exactly what we capture in the model too. We will see how we can create a graphical editor where you will be able to lay out this information, the same information in the model in a graphical way, but the graphical representation carries no information, no extra information.
In the same sense that you can first input like the last step, for example, it doesn't
It doesn't mean that because we input it in the model, the welcome message first, that it's the first step in our sequence. It has to, the generator has to look into more information. For example, what you said, that it has no incoming connections.
Yes.
And therefore, it should be first.
Yes, when it tries to generate procedural code, it will need to find a starting point. So then we will need to instruct it to start with any actions that have no incoming transitions. Now, the question is, what happens if we have two of them, right? Then we need to write constraints for our models and say that in every model we need to have at most one or exactly one action that has no incoming transitions, because we expect one entry point. And we're going to see how we can express such constraints tomorrow. Does this answer your question?
Yeah.
Any more questions? No? Okay. So just in preparation for this afternoon, what we have is we have four decks of practical slides for this course. So you need to work with your team. Start with the slides from practical one. It lists some problems here. The first problem also has a reference solution so that you can see how you can create a meta model from a problem description. This first practical is on pen and paper only, so you don't need the Eclipse. You can just get together in groups and you can kind of talk about the languages and you can draw them on paper. Now the second practical, and feel free to progress as much as you can with these two practicals. So if you finish the material from the first practical, move on to the second one. The second one goes into E-core and emphatic and essentially asks you to create the meta models that you have designed using pen and paper in Eclipse, right? So to type them in using emphatic and to then instantiate them and create models that conform to them, right? And using what we've talked about today, you should be able to complete the first two practicals, right? But how much you manage to go through it really depends on the amount of discussion you have, how much trouble Eclipse gives you, and everything, right? But in principle, you should be able to complete the two practicals. For the third practical, you will need tomorrow's lecture. Okay. So about the practicals, don't wait for me to be around. We'll come back here at 2 o'clock, I believe. 1?
No,
yes.
I'm sorry for the heating issue of the room. We have expected it to be fixed quite quickly, but it seems not. The room just there, R002, is free.
Okay.
And there is heating, so I suggest that we move there.
Yes.
Sorry again.
Yes, let's do that. So we're coming back at 1? 1 o'clock. So get together in your groups. I will come around and see if you're not in a group, but try to get into groups of 3 as we discussed, and start working on these exercises. We won't need to record the practical because there will be no lecture. Really, it will just be you working and me walking around and helping you out with any questions you may have. Okay? Feel free to work at your own pace. If you'd like to take your team and go have a coffee somewhere and work there, do that. You don't have to be in the room. Okay? Great. See you in the afternoon.